this tutorial, we will implement a color palette matching effect in Max. So the idea of this tutorial is that we create a random color palette, and then for a given input video, each pixel is matched to the closest color in that random palette. And then essentially we're recreating the input video or the input texture with the colors from the color palette. The tutorial consists of 4 parts. In the first one, we will create a random color palette. In the second one, we will take a look at how to access the colors from the palette. Then we will implement the algorithm that gives us the closest or the nearest color from the input texture. And in the fourth one, we will apply some dithering so it looks a bit smoother. I am starting with a jit world object as our rendering context. Here I have a jit p window to monitor what we're doing, and here I have an input video. Okay, starting with the first part, creating a random color palette. I will use a jit.noise object, free planes, float 42. Let's set this to 1 by 1. Then I want to work with textures, so we will use this as an input for, no, not that one, for a texture. Let's make this, oh, sorry, that was wrong. Let's make this full HD. Also say a depth 0 so it doesn't change, and we use, sorry, type float 32. Then we can connect them. I will also create a jit p window so we can see the color that we're creating. And now if I'm banging this, I'm getting a random color, but I also want to change the number of colors within the palette. To do this, we can say, so we can use a message, say dimension $1. So we have a variable here, 1 here, and then we'll also bang this one. Then, yeah, we can set the number of colors in the palette here, and then also change the colors here individually. Okay, that was easy enough, I guess. Coming to the second part, now I want to access those colors from a jit.gl codebox. So I will create this one. jit.gl.pix codebox. And the rest of the code will just live in here. Okay, so in order to access individual colors, we need to take this one as an input and then sample this texture at the given positions. And in order to do this, first we need to know how many colors we're using or how many colors we have within our palette. So in order to do this, I will create a parameter. Let's call this one numColors, set this to 1 for now because it doesn't matter. And I will also set an output. This can be just 1 for now. Then we can connect this one in here. We can connect the input in here, turn everything on, and now we can see our output that is white here. Maybe we can also, yeah, I will duplicate this one, put it in here, and then I use a jit bang object. So we're constantly banging this texture. And now this is running independently of this video playing. Okay, continuing here. So what are we trying to do? We want to access individual colors here. So we need to set the number of colors, and the number of colors, of course, here is equal to the number of colors we have here. So we can do something like trigger integer integer. Connect this here, and then create the parameter outside. Let's call this num colors, or I mean, we already call it that. Then we connect this here. And now we are simultaneously setting this parameter here, the number of colors, and the number of colors for our color palette. Okay, in order to access this, we can say something like palette color. Then we need to sample what's coming out of here. So we can say nearest, and now we're using the nearest operator. So the sample operator would be interpolating between colors, but the nearest just takes the nearest color as it is, which is exactly what we want here. And we can say something like into, because we want to plug this into the second input. And then we need a, what do we call this? A position. I mean, we could just say, I will create another parameter, which we will just use temporarily. So this one is called, I don't know, color index. And we can set this to 0 for now. And the idea now is, okay, if we take a look at this one, and this one has 5 colors now. So when we're using, or when we're sampling it, we're using normalized coordinates. So we have to divide this whole thing. So we have the minimum at 0 and the maximum at 1. So this one starts at 0, this one starts at 1/5, this one starts at 2/5, 3/5. This is pretty hard for a non-native speaker. And this one starts at 4/5. So in order to access the individual colors, we need to say that we're taking the color index we want, and we're dividing it by the number of colors we have here. And then we can set this here. Of course, we need to patch this one in here. Set this one again. Okay, now, where is it? Color index. Okay, if index is 0, we want the first one. If index is 1, we want the next color. But as you can see, it's not quite working, because what we're essentially doing here is we're getting the coordinates at the start, so right at the edge. So in order to get rid of this, I will create an offset. So we move from the beginning of the color bin to the center of the color bin. So offset equals 1 divided by the number of colors. So this essentially gives us the size of one of those color bins, but I only want to move half the size of one color bin so that I'm in the center of each color bin. And then theoretically, hopefully, if we're adding this in here, okay, I will make more. I'm already running out of space, as usual. Okay. So hopefully this works now. So this is the first bin, second, third, and so on. And even if we say something like 16 and I want to have this color, this should be bin 3. Now we have this color. So the last one should be bin 15. Yeah, looks good. So with this technique, you can access individual colors of this color palette. I guess we can then move on to the second part of the tutorial. Or no, it's already the third part, getting the closest color. So what I want to do now is for each pixel. So you can imagine each instance, so each line of code is running on each pixel in parallel. So for each pixel, I want to go over the whole color palette and then see which color matches our current color the closest, and then use this one. So in order to do this, we need a for loop, because I want to iterate over all the colors within our color palette and then see which one is the closest. Okay, so for I equals 0, we're starting with 0. Then I is smaller than the number of colors. So we're iterating over all the colors, and then we're incrementing by 1 after each iteration. What do we want to do now? First, we want to get the color itself. So we can move this one into the for loop. And again, running out of space. Okay, this one into the for loop. Then we don't need this color index anymore, because the color index will just be I. So we're using I. And we're starting with 0 up to the number of colors we have in here. And so each iteration gives us one of the colors out of the color palette. Okay, so now we have RGB color information, but I want to use HSL, so hue, saturation, and lightness. So in order to get this, I will transform this and say palette HSL equals the current color, but we're using it as an input for this function, so RGB to HSL. Now we transformed it. So what we could do is we could just use the hue or just the saturation or just the lightness, or we can use a combination of all of them to see how close the colors are matching. I think I will use a combination. So in order to do this, let's also create some weights for them, because maybe I want to have more of an emphasis on the hue and on the lightness and not so much on the saturation. So I will create weights that will deal with that. Okay, WH for weight hue. Then for saturation and for lightness, and I guess I can already set this. So now we can see that hue is the most important thing, followed by lightness, and then saturation is the least important thing. Then I guess we can look into the difference between the colors. So the difference between the color that's coming in and each color from the palette. So to get the color that's coming in, we can say, let's create a variable, call this one video in. This is in 1. Then we can say something like in HSL. This is again applying this function to our video in. And now we can do the comparison. We can say, so we're looking at the difference between the current pixel and the color we're getting from the palette. So we can do this for all 3 of them. So we can say delta H for delta U is the input color. So the X component of this one minus the X component of this one, because the X component in this case is the hue. But the problem here with the hue is that it's a circular thing. So it wraps around. So we're starting from 0, then going to 1, and after 1 it just comes back where it started with 0. So what we should do is taking the minimum of the current delta h that we just got here and 1 minus the current delta h. So this will prevent us getting a delta or a difference that is greater than it actually should be because of the wrapping around thing. Okay, then we can say delta S for delta saturation, and this is essentially the same thing. But now we're using Y because, so the second channel in HSL is S saturation, so we can take the Y component, which is the second channel, and then I will just copy this, call this delta L. So this is the difference in lightness, and this will be then the Z component. So now for all of the 3 components, we get the difference between the input pixel and in each iteration for all of those colors in the color palette. Okay, then I will compute like so this is the individual deltas, and now I will compute the kind of the main delta, like the combination of all of them. Let's call this one current delta. And now we will use the weights we created earlier. So we can say, first I want to square all of them because squaring does 2 things. First, this could also be a negative number. So squaring turns it into a positive number, and squaring also puts an emphasis on the values that are closer to 1. So there will be an emphasis if there's a big error, and smaller errors kind of will be neglected this way. Okay, so we can say delta H multiplied by delta H. So this is essentially squaring it, and then we can apply the weight we created here. Then, yeah, it's essentially the same thing 3 times. So now we're doing it for the saturation, saturation here, saturation here. And of course, once again, for, whoa, there I am, for the lightness. So delta L, L, and L. So now we have the current delta is now a combination of all 3 of them, hue, saturation, and lightness, with the weights that we created. And if we want to say, okay, we only care about the lightness, we could set both of them to 0. Or if we say we only care about the hue, we could also reduce this. So this gives us a bit more control. The thing is, now we're just doing this iteration, and for these iterations and for, oh, I just saw there is a mistake. This one shouldn't be multiplied, but plus equals 1. Okay. Yeah, so now for each iteration, we're getting a different value, but each iteration is done on every frame. So there is no comparison happening. And in order to see which of those colors, because now we're just looking at, okay, what's the delta for, or what's the difference for the current pixel and each color of the palette. And in order to see which delta is the smallest, because if this current delta here, if this one is very large, this means that there's a big difference between the pixels we're comparing, and the smaller this one gets, the closer they are in color or in lightness or in whatever we're interested in with those weights. So the idea is that we're iterating over all the colors on the color palette and then always setting a new delta to then get the smallest number. So what I mean by that is, okay, I'm already running out of space. Maybe I can also make some space up here. I don't need this one anymore. We could also plug this one in here. And maybe also put this down here. And now I gained 0.5 centimeter. Not sure if that was worth it, but yeah. Okay, back to the coding. Yeah, I will create a global delta variable and set this to be a very high number. What's that? 100,000. And then we can do the comparison. So for each of the colors in the color palette, we get the difference between the input pixel and the color. And then we can say if this current difference that we just computed is smaller than the global, then we can say that the global is the current. So imagine we're starting with 100,000 here, then we're looking at the first color, and then, I don't know, the difference between the first color and the pixel we're working on is something like 5, then we see, okay, 5 is obviously smaller than 100,000, and then 5 will be the new global delta. Then maybe in the next pixel, the delta is something like 6, which is not smaller, so 5 will stay the smallest. Then we go to the next one. Maybe this is 4, which is smaller than 5, so it will be set to this value. So this is a pretty neat algorithm to find the smallest delta. But this is only half of what we need. Knowing which delta is the smallest is not all that we need. We also need to apply this color to the current pixel we're looking at. So in order to do this, we need another global variable. Let's call this one color index. Let's set this to 0 for now. And this will tell us the index of the color in the color palette, so we can then apply it to the current pixel. So if this delta changes, we also want to know which index this color has. And in order to do this, we can just say color index equals I, because as I, in this case, just represents like which color we're on in the color palette, we can use it to set the color index. And yeah, if the delta is smaller, this will also be changed. And if it's not smaller, it just stays at the smallest delta, which is exactly what we want. That was a lot. Now that we have the index here, we can then apply it. So we can say, okay, we used this up here. So maybe we can say something like final color. And then we can again use the function we used up here. But instead of using I here, we can now use the color index. Okay, and then we can say final color is our, final color is our output. Yeah, and then I also got some errors, but I think they're not relevant anymore. Yeah, so to recap, what is this algorithm doing? It's looking at, so for each pixel in here, it's going over all the colors we have in our color palette, and then it chooses the one that is the best fit and then applies it. And the best fit can be set here. So now we're doing an emphasis on the hue, but we can also set this to 0 and put an emphasis just on the brightness of the pixels. Now it looks a bit different. But I really like using the hue. Maybe let's do something like this. Yeah, you can play around with those values. And of course, if I'm changing this, the colors that get applied also change. We could also say we don't want to use 5 colors. We want to use 32 colors. And then this also works. I mean, I guess you have to be careful if this number gets too high, then because yeah, this for loop is done for each of those pixels. And if you have an input texture that's full HD, like I'm doing it here, then the higher this number, the more computationally expensive it gets, because now it has to do for each pixel like this thing 30 times, 32 times. But if I'm using 200, then for each pixel, it has to be done 200 times. But of course, using more colors also creates more interesting results, I guess. I mean, depending on what you're going for. Okay. Yeah, I guess now we can come to the fourth part, which is dithering. Because as you can see, I mean, it highly depends on the kind of input texture or input video you're using. So if this has a lot of colors, or just like, it depends on the number of colors in the input video, and it also depends on compression artifacts. Because here, I'm not sure if this is visible. It sometimes, depending on the input video, it can get a bit blocky. And in order to reduce these harsh transitions from one color to another, we can introduce dithering, which means that we're applying a noise function to our lookup, to our color lookup, to make the transitions a bit smoother. Okay. This will be clearer once we're implementing it. Yeah, in order to apply a noise function, we could either use another jit.noise and turn this into a texture, or we can create our own noise with a noise function from the book of shaders, which I'm using here, which I'm getting from this here. So I'm copying this. So in jit.gl.pix, functions have to be declared before parameters. So we can copy this in here and then change it so it fits the syntax here. So let's call this one random. Input is st. So we're inputting a vector into this, and then it does a bunch of, it applies a bunch of operations, and then we get some noise as an output. This looks good so far. Okay, this should be just vec and not vec2. No errors. Okay, let's see if this worked. So let's copy this and set it as our output 1. And as an input, we can just use normalized coordinates. And if I'm spelling it right, it should work. Yeah, okay. Now we have some white noise going on here. And in order to use this, so now it is static. I want it to change over time. So I will create another parameter. Call this one time. And then we can add this in here. Which didn't change a thing. But if we create a message box, $1 for time, to access this variable from the outside, where is it? Down here. Then we can use a jit.time object. And now for each frame, we get a different noise. Of course, you can see some regularities in there because we're using sign and dot product, but I guess it's random enough for our use case. Okay. So now we confirmed that it is working. Now we just have to apply it, and I will apply it to the input video. So let's create a new variable here. Let's call this one n for noise. And this one is our random function. Essentially the thing we used earlier. So normalized coordinates plus our time input. And in order to apply it, we need to scale it first. So I want to scale it to be the size of one bin of our color palette. So in order to do this, we can say n equals n times 1 divided by the number of colors we have in here. So essentially the same we did with the offset. So now, but now it only goes in one direction. So maybe, yeah, I will do n. So now this n here goes from 0 to 1, and multiplying it by this essentially scales it to the size of one of those color bins. But this means that it only goes into one direction. So if I'm subtracting 0.5, this means that it's now going from minus 0.5 to 0.5. So it will go either to the left bin or to the right bin. And then we can also scale it by some factor, so it's a bit smaller. And now I think I can just add it in here. Okay. I'm not sure if this was clear, but yeah, if I'm looking at this, setting this to 0. Maybe also change this a bit, and now setting it to 0.5, you can see that we get more details. So if we have these harsh edges between two colors, now there's a bit of randomness which color the algorithm is going to choose. So I mean, with this input video, I'm not sure if it is needed, but if you're using other videos with less color information, you can see blocks of color forming, and applying this dithering algorithm helps to prevent that. Okay, I think that's almost it. Let's look at 200 colors. Yeah, very nice. Yeah. I will do one last thing. So now we only have the effect, but it would also be nice to crossfade or to interpolate between the original video and the effect. And to do this, we can say mix here in the output. And we're fading between the input video and the final color, or maybe call this one effects color. And then we can create another parameter up here, call this one amount, set it to 0.5, and then we can use it down here to interpolate. And then, yeah, we can access this from the outside. So if this one is 0, it's just the original. And if this one is 1, it's the color palette. And then we can use anything in between. And I think this is where the magic happens, because, I mean, yeah, of course, I used a very nice, crisp looking input video. So the colors are already looking great. But now when I'm increasing this, it kind of gets this Technicolor feel and look to it, which is pretty nice. It's also nice to do this at 0.5 and then try using different color palettes. What we could also do is use a jit bang object and create a different palette for every frame, which is kind of trippy, but also a very nice effect. Yeah, and depending on what you're going for, you can adjust these weights. You could also, I mean, next step could be not using a random color palette, but creating your own color palette. Like you could use another video to create a color palette and then apply it to this one. Yeah, so you can and should get creative with this one. Yeah, that's essentially what I wanted to show you. I hope you found this useful and thank you for watching.